Have you ever pondered the secrets of the universe, or toyed with the idea of time travel? The cosmos holds a myriad of mysteries that have intrigued mankind for centuries. Enigmatic phenomena like black holes, the Big Bang, and the elusive concept of time travel have all left us scratching our heads in bewilderment. In the midst of these complexities, one theory has held a lantern to the darkness, illuminating our understanding of the universe and its intriguing mechanisms. This theory, proposed by one of the greatest minds in history, has been a cornerstone in our quest to decipher the universe's most profound secrets. So, what is this key that unlocks the universe's enigmatic riddles? It's none other than Einstein's theory of relativity, a groundbreaking concept that forever changed how we perceive the universe and our place within it. Enter the world of Albert Einstein, the mastermind behind the theory of relativity. Einstein's theory of relativity, in its simplest form, revolutionized our understanding of space, time, and gravity. Let's break this down into two parts. The first part is called special relativity. Einstein proposed this in 1905, and it stems from a very basic idea. He suggested that the laws of physics are the same everywhere, for everyone. It doesn't matter if you're at the edge of the universe or right here on Earth. The laws that govern the physical world are consistent. This means that whether you're standing still or moving at a constant speed, your perception of physical phenomena remains the same. But Einstein didn't stop there. In 1916, he introduced the second part of his theory called general relativity. This is where gravity comes into play. Einstein proposed that gravity is not just a force between two objects, as Sir Isaac Newton had suggested, but rather it's the result of objects warping the very fabric of space and time around them. Imagine a bowling ball resting on a trampoline. The weight of the ball causes the trampoline to sag or warp. This is how massive objects like planets and stars warp the space-time around them. Now, here's where things get really interesting. This warping of space-time affects how things move and even how time flows. That's right, time itself can be influenced by gravity. The stronger the gravitational field, the slower time runs. This is why time on a mountaintop runs slightly faster than at sea level, though the difference is minuscule in everyday life. And what about light? Well, light always travels in straight lines, but in a curved space-time, those straight lines appear to us as curves. So, light bends as it travels through this curved space-time. This is what we call gravitational lensing, a phenomenon that has been observed and measured. So, in essence, time slows down near massive objects and light bends as it travels through this curved space-time. But you may ask, how do we know this theory holds water? Well, the proof of the pudding, as they say, is in the eating. In the case of the theory of relativity, the proof was in observing. Let's travel back in time to the year 1919. Picture a solar eclipse. This isn't just any solar eclipse, but one that would become a landmark moment in our understanding of the universe. British astronomer Sir Arthur Eddington, armed with his telescopes, observed the light from distant stars as it passed our sun. According to Newton's laws, this light should travel in a straight line, but lo and behold, it didn't. The light got bent, deviating from its path. It seemed as if the sun's gravity was tugging at the light, pulling it off course. This was exactly what Einstein's theory of relativity had predicted. The universe, it seemed, was playing by Einstein's rules. Fast forward to the present day. You might be thinking, sure, bending light is impressive, but how does this theory affect me? Let's consider something you probably use every day, GPS technology. Your car's navigation system, the map on your phone, they all rely on GPS. But here's the kicker. GPS wouldn't work if we didn't take into account the principles of the theory of relativity. You see, the satellites that power GPS are moving fast and are far from Earth's gravitational pull, which means time ticks off slightly differently for them than it does for us down here. Without correcting for this difference, your GPS coordinates could be off by kilometers, and you'd probably end up lost in the middle of nowhere, wondering why you didn't just ask for directions at the gas station. So next time you use your GPS to navigate, remember it's all thanks to a man named Albert Einstein and his groundbreaking theory of relativity.